Welcome to another lecture on the course on 3G and 4G wireless communications. In the last lecture we finished our performance comparison of wired and wireless communication systems. In particular, we saw that the performance of wireless communications is far worse compared to the performance of wired communication systems, especially because of the destructive interference. For instance, we saw that for a bit error rate of 10 power minus 6, we need 10,000 times more power in a wireless communication system compared to a wired communication system. Alright, that is, if in a wired communication system I need 1 watt, in a wireless communication system I need 10 kilowatts. Alright, and we said the reason for this, at least from the expressions, from the bit error rate expressions we derived, is as follows. Because the wireless communication system bit error rate decreases only as a function of 1 over SNR, while the performance of a wired communication system decreases exponentially in SNR, that is, it is e power minus SNR. So, it decreases very fast, so that even for small SNRs it is extremely low. And another very interesting reason we found out for the poor performance of the wireless communication system is, we said the performance of a system is bad when the receiver power is much smaller than the noise power. That happens when A square P, which is the received power, is less than sigma n square, that is the noise power, which means A is less than 1 over square root of SNR. Alright, and we said the probability that A is less than square root of 1 over SNR is precisely 1 over SNR. Alright, hence the bit error rate expression that we saw, which is 1 over 2 SNR, is nothing but the probability that approximately equal to the probability that A is less than 1 over square root of SNR, which is what we said is a deep fade event. What is a deep fade? A deep fade is a condition where the destructive interference of the wireless channel due to the multipath propagation is so severe that you receive almost no signal power, and that happens with a probability 1 over SNR. Hence, the bit error rate is 1 over SNR. So, the bit error rate is nothing but the probability of the deep fade in a wireless communication system. We also said, so deep fade is nothing but the probability of destructive interference, and we also said we want to tackle this problem. This is a problem that is arising due to fading. Which is a deep fade. We said we want to solve this problem to improve the performance of a wireless communication system, and we realized that the solution is to introduce multiple links. Since the wireless communication system goes into a deep fade when one of the link is in a deep fade, if we introduce multiple links, what will happen is, even if some of the links are in a deep fade, the rest of the links can be used to convey the information reliably. So, I can improve the reliability of my system by increasing the number of links, and this we said is a powerful idea known as diversity. Alright, and we started analyzing a system with receive antenna diversity. We said we have 1 transmit antennas, L receive antennas. So, we said that system can be represented as Y1 equals H1x plus N1, that is the signal received at receive antenna 1 is H1, which is the coefficient between transmit antenna and receive antenna 1, times x, which is the transmitted signal, plus N1, which is the noise at receive antenna 1. Similarly, Y2 equals H2x plus N2, so on and so forth until YL equals HLx plus NL. We said we can represent this in vector notation. More specifically, we said I can represent Y1, Y2, YL as an L dimensional vector, H1, H2, HL as another L dimensional vector, and N1, N2 up to NL as another n dimensional vector N bar, and hence the net system model is Y bar equals H bar X bar plus N bar. Okay. So, with this we will go into today's lecture, in which we will analyze the performance of this system, of this receive antenna diversity system. So, let me start with today's lecture, which is analysis of receive antenna diversity system. Okay, analysis of RX antenna diversity system. We said the system model is y bar equals h bar x plus n bar. Let me refresh your memory. Y bar is the L dimensional receive vector y1, y2, yl, where y1 is the signal received at antenna 1, y2 is the signal received at receive antenna 2, so on so forth until yl is the signal received at antenna L. H bar is the L dimensional channel coefficient vector, where h1 is the fading coefficient between transmit antenna and receive antenna 1, h2 is the fading coefficient between transmit antenna and receive antenna 2, so on so forth. HL is the fading coefficient between the transmit antenna and receive antenna L, and similarly the noise vector n bar at each receive antenna. Now, signal detection, and also let me mention here that the expected value of noise, that is the noise variance, that is the power of the noise on each receive antenna is sigma n square, which means all the receive antennas are symmetric and the noise power at each receive antenna now is sigma n square. Alright. So, now let me start analyzing this thing. So, let me start analysis. Let me go to the next page. Let me start analysis with signal detection. Now, how to detect the signal in this system? I have y1, y2, so on and so forth up till yl. These are the signals received at L receive antennas. At the L receive these are the signals received at the L receive antennas. What I will do is now I will combine these signals to detect my transmitted signal X. So, what I will do is I will combine these received signals. So, I will combine these received signals as follows. I will take y1, weigh it by w1 conjugate. I will take y2, weigh it by w2 conjugate, plus so on so forth. I will take yl and I will weigh it by wl conjugate. So, what am I doing? I am doing w1 conjugate y1 plus w2 conjugate y2 plus until wl conjugate yl. I am weighing each yi by wi conjugate and I am adding all these received signals up. So, I am combining them linearly so that I can detect the transmitted signal X. Remember, the transmitted signal X is present in each one of these signal copies. Remember, these are signal copies, we are receiving L copies. So, we have to combine them to detect the transmitted signal X. That is the essential idea. So, we can represent this as succinctly using vector notation as W1 conjugate, W2 conjugate, so on up to WL conjugate times y1, y2, so on up to yl. Remember, this y1, y2 up to yl is nothing but the vector of received signals across the L received antennas, which is y bar, and now I can succinctly represent this as w bar Hermitian y bar, where w bar is the vector w1, w2, so on up to wl. Alright. So, what I said is we are linearly combining the received signals as w1 conjugate y1, w2 conjugate y2, so on up to wl conjugate yl. I can represent this succinctly using this matrix notation, which is nothing but w bar Hermitian y bar. Now, let me remind you of the properties of matrices, if W bar is W1, W2, WL, then W bar Hermitian is nothing but the transpose of W and then the conjugate, alright. So, if W bar equals W1, W2, WL, then W Hermitian is first I take the transpose, that is the column vector becomes the row vector, that is W1, W2, so on up to WL, and then I take the conjugate W1 conjugate, W2 conjugate, so on up to WL conjugate. So, W bar Hermitian is nothing but the row vector W1 conjugate, W2 conjugate, WL conjugate, and so this is nothing, and the receiving that we are doing is nothing but taking Y bar and multiplying it on the left by W bar Hermitian. This has a name when I am linearly combining the signals at the output of receive antennas in a receive antenna diversity system or in a system with multiple antennas. This has a name, this is known as beam forming, right. By combining these Y1, Y2, YL, which are the received signals across the L receive antennas, I am doing technically what is known as beam forming, and the vector Y, a vector W bar is known as the beam former. So, I am doing beam forming when I am combining the signals, and the vector W bar is known as the beam former or the beam forming vector, alright. So, now I am doing beam forming, which means my received signal is W bar Hermitian Y bar. Now, we already know that Y bar equals H bar X plus N bar. Now, I will substitute this expression for Y bar here, hence my output, my beam former output is nothing but W bar Hermitian into Y bar, and Y bar is H bar X plus N bar. So, I am doing beam forming and my beam former output is W bar Hermitian Y bar is H bar X plus N bar. So, my beam former output is W bar Hermitian H bar X plus N bar, alright, and that can be represented further expanded as W bar Hermitian H bar plus W bar Hermitian N bar, W bar Hermitian X H bar X plus W bar Hermitian N bar. This first component is nothing but the signal component, and W bar Hermitian N bar, which is a combination of the different noises at the different receive antennas, is the noise component, alright. So, my output of the beam former is W bar Hermitian H bar X, which is the signal component, plus W bar Hermitian N bar, which is the noise component, alright. So, now I can write this as, let me rewrite this over here, W bar Hermitian H bar X plus W bar Hermitian N bar. Let me compute the signal to noise ratio. The SNR is nothing but the signal power divided by the noise power, alright. The SNR, the signal to noise ratio of the output of the beam former in this multiple receive antenna system is signal power divided by noise power. Now, let us first compute the signal power. The signal is W bar Hermitian H bar times X. So, this is like some constant multiplying X. So, the signal power is nothing but So, signal power is nothing but the magnitude of this constant W bar Hermitian H times the power in the signal, which is P. Remember, we also had something similar to this in the single link wireless communication system. The received signal there was H times X. We said the power in the received signal is magnitude H square times the power in X, which is P. Hence, the signal power is was A square P. Now, we have W Hermitian H bar times X, because this has multiple links, this is a multiple antenna system, we are combining the signals. The received signal is W bar Hermitian H bar times X. So, the signal power is nothing but the magnitude of W bar Hermitian H bar square times P. Alright. So, the received signal power is W bar Hermitian H bar square times P. Alright. Now, let us do something slightly more difficult, which is to compute the noise power. That is not obvious from what we have written above. We said the noise is effective noise at the output of the beamformer is given as W bar Hermitian N bar, right. The effective noise at the output of the beamformer is a combination of all the noises across all the receive antennas, that is nothing but W bar Hermitian times N bar. Alright. Now, we will compute what is the power of this noise, or in other words the expected. Remember, this is a random quantity, each N1, N2 up to NL is a random quantity. I am combining all these quantities. So, the output is another random quantity, which means the output power is expected magnitude W bar Hermitian N bar square, which can also be written as expected W bar Hermitian N bar into the magnitude is nothing but the quantity into its complex conjugate. So, I can write this as W bar Hermitian N bar conjugate. Okay. Now, let me do the long way of deriving this noise power. We know W bar Hermitian N bar is nothing but W1 conjugate N1 plus W2 conjugate N2 plus W L conjugate NL. Alright, W bar Hermitian N bar is nothing but W1 conjugate N1 plus W2 conjugate N2 plus so on so forth until WL conjugate NL. Now, if I want to look at the magnitude, I need square, I need to multiply this quantity by its conjugate. So, I will take this quantity W1 conjugate N1 plus W2 conjugate N2 plus so on plus WL conjugate NL times its conjugate. Now, conjugate of W1 conjugate N1 is nothing but W1 times N1 conjugate, because the conjugate of a product is the product of the conjugate. So, I will write this as W1 N1 conjugate plus W2 N2 conjugate plus until WL NL conjugate. Now, this can be written, this is the product of two summations. I will use succinct summation notation here, because otherwise it is too lengthy to write it. This will have terms which are of the form, which are the direct terms, which is each term with its conjugate. So, we will have terms of the form summation I equals 1 to L Wi conjugate Ni into Wi Ni conjugate, which is nothing but magnitude Wi square magnitude Ni square, plus I will have the cross product terms, which are nothing but summation over I summation over j I naught equals j Wi Wj conjugate Ni conjugate times Nj. Alright, so I am representing this product as the sum of direct components, which are Wi conjugate Ni times Wi Ni conjugate. When you take the product, it is simply Wi conjugate, which is magnitude Wi square, Ni conjugate, which is simply magnitude Ni square. That those are the direct terms, and then we have several cross terms. Now, if I take the expected value of this whole thing, you can see that the cross terms which are Ni and J are 0, because expected Ni and J conjugate is nothing but expected Ni times expected Nj conjugate, because the noises at the different receivers are independent, and we know from the properties of independent random variables, that is if x and y are independent random variables, then expected x y is nothing but expected x times expected y, but expected Ni and expected Nj are both 0. So, this is 0 times 0, which is 0. So, this term over here to the right is identically 0. The only term that survives is expected magnitude Wi square, magnitude Ni square, and each expected magnitude. So, let me write this down. The noise power, the net noise power is expected summation magnitude Wi square, magnitude Ni square. This I can write as summation, because Wi square is a constant, magnitude Wi square is a constant. So, that will come out of the expectation. I can write this as magnitude Wi square expected Ni square summation over I. This is nothing but each expected Ni square is equal, that is the power in the noise at each receive antenna, that is sigma n squared. So, this is simply sigma n squared into summation magnitude Wi squared, and we know the summation magnitude Wi square is nothing, it is simply the norm of this vector, it is simply the magnitude of the vector. If I am taking the sums of the squares of the magnitudes of each of the components of a vector, that is nothing but the norm square of that vector. Alright. So, that is simply the length square of that vector. So, this is simply sigma n square norm W bar square, and norm W bar square is nothing but W bar Hermitian W bar. So, this is simply sigma n square W bar Hermitian W bar. Okay. This is the main result that we want. So, the noise power, let me write this down clearly what we have. Noise power at the output of the beam former equals sigma n square times norm W square, where W bar is the beam forming vector or the beam former. Alright, so we have derived the noise power at the output of the received beam former. We said it is the combination of the noises across all the L receive antennas, and we said it is not straightforward to compute the noise power, but we went through a derivation to compute that net noise power, and we said the net noise power is nothing but sigma n squared into magnitude of the beam former. Alright, so that is the net noise power. So, now let me go back, remind you, we have an expression for signal power. Signal power is magnitude W bar Hermitian H bar magnitude square times P. The noise power is nothing but sigma n square magnitude W square, hence the signal to noise ratio SNR at the output of the beam former equals signal power divided by noise power, and we said signal power is nothing but W bar Hermitian H whole square into P divided by sigma n square into W bar Hermitian W. So, the noise power at the output of the beam former is nothing but magnitude W bar Hermitian H bar magnitude square times P divided by sigma n square magnitude W bar Hermitian into W bar. Alright. So, we have successfully derived a signal to noise power ratio at the output of the beam former in terms of the beam forming vector W bar. Now, let me illustrate to you another technique to compute the power in the noise, because this is important, because we will do this manipulation several times. So, let me illustrate to you another technique to compute the noise power, which is also useful to you in many other contexts. So, we said the noise vector n bar can be is nothing but the vector n1, n2, so on up to nl. The noise vector n bar contains L components, that is the L noise components across all the receive antennas in this multiple receive antenna system. Let me compute n bar Hermitian. Now, n bar Hermitian, remember that is why you need a background of linear algebra, because we are going to use wireless communications. We extensively use the theory of random variables, linear algebra, matrices, introductory theory on communications, digital communications, so on and so forth. So, it is very rich and advanced, and I urge you again to refresh your concepts of matrix theory, linear algebra and so on, alright, because we will use them extensively throughout this course, alright. So, n bar Hermitian is nothing but n1, n2, nl, the vector n1, n2, nl times, now n bar Hermitian is nothing but transpose, which is the row vector, and the conjugate. So, that is n1 conjugate, n2 conjugate, nl conjugate. I will write down this as the matrix. Look at this. This is the first row, first column of this is n1, n1 conjugate, which is magnitude n1 square. Similarly, n2, n2 conjugate will be on the second row, second column, that is magnitude n2 square. So, the diagonal is magnitude nl square. The other elements are of the form n2, n1 conjugate, n1, n2 conjugate, so on so forth, which are precisely the cross terms that we saw. Alright. So, if I look at n bar Hermitian, along the diagonals I will have the direct product terms, along of the diagonal I will have the cross terms, and we said if I take the expectation of this matrix, if I take the expectation of this matrix, let me write that expectation down here, that is nothing but along the diagonals I will have sigma n squared, sigma n squared, sigma n squared, and along of the diagonals I have the cross terms, but the cross terms are of 0, because if I take expected n1 n2 conjugate, that is expected n1 times expected n2 conjugate, which is both are 0. So, along the off diagonal term, all the off diagonal terms here are essentially 0, which means expected n bar Hermitian is nothing but a matrix which contains sigma n squared, all elements sigma n squared along its diagonals, and the rest of the terms are 0, and you will recognize this immediately as nothing but sigma n squared times the identity matrix. So, expected n bar Hermitian is nothing but a matrix which is sigma n squared identity. Now, I will compute the noise power as nothing but, remember I am going back to my problem of computing noise power. Noise power is nothing but expected W bar Hermitian n bar times W bar Hermitian n bar conjugate. I can write this as expected W bar Hermitian n bar times n bar Hermitian W bar. Now, I can move the expectation operator inside to write this W bar Hermitian expected n bar Hermitian W bar. We saw expected n bar Hermitian is nothing but sigma n square identity. So, that is just proportional to the identity matrix. So, that will simply be sigma n square, because any matrix times identity is itself, this is simply W bar Hermitian W bar, which is sigma n squared norm W bar square, same as what we desired earlier, except that this uses matrix notation directly. So, it is a very elegant way to derive the same result. Remember, we derived this result earlier, alright. If you go back 2 pages, we said the noise power is sigma n square W bar square, norm W bar square, but we derived this using the elaborate or the brute force way of directly expanding the summation. Instead, a more elegant way is to use matrix notation, and using matrix notation this can be very easily derived in a relatively straightforward way as sigma n squared norm W square. This is the noise at the output of the beamformer. Hence, the signal to noise ratio is nothing but SNR is nothing but it is magnitude W bar Hermitian H square P divided by sigma n square W bar Hermitian W bar. Alright, this is the signal to noise power ratio at the output of the beamformer. Let me refresh your memory. We said we want to consider a system with diversity. One form of diversity is to have multiple receive antennas. Specifically, we are considering a system which has L receive antennas. We are receiving L signals y1, y2 up till yl. We are combining those signals using vector W, which we said which is the beamforming vector. The process we said is beamforming. The signal power at the output of the beamformer we said is magnitude W bar Hermitian H bar square P, and the noise power is sigma n square W bar Hermitian W. Alright. So, this is the signal to noise power ratio at the output of the beamformer. Now, my problem is very simple. The problem is simply to maximize the SNR at the receiver. Remember, we have now talked a lot about this W bar vector, but we have never talked about how do we choose these weights, how do we choose this vector W bar, and that is simply I want to choose my W bar such that this receive SNR is maximized. So, my aim or choose, I will write my strategy to choose W bar is such that W bar, choose W bar such that W bar maximizes the SNR. That is, choose W bar such that W bar maximizes this SNR, that is at the output of the receive beamformer. Alright. So, I want to choose a beamforming vector W bar such that I want to maximize the SNR in this multiple receive antenna diversity system. Notice here in this SNR expression that I can isolate the term corresponding to W bar and write this as SNR equals W bar Hermitian H bar magnitude square divided by W bar Hermitian W bar, alright, and into P over sigma n square, and this is the term I want to maximize. This on the right hand side, P over sigma n square does not depend on the beam former W bar. The only part that depends on the beam former is W bar Hermitian H magnitude square divided by W bar Hermitian W bar. So, now I want to maximize this, maximize. So, I want to maximize this SNR. In other words, I want to choose W bar such that this value is maximum. Now, I will do a slight trick. Observe that, for instance, let us start with this. Let us say I find that optimal W bar. Let us say some angel gives me that optimal W bar which maximizes the SNR. Now, let us say I scale that W bar by k. So, what is happening? Someone gives me this optimal W bar, I scale that W bar by k, then the SNR is nothing but magnitude W bar Hermitian H bar square, which is k square times magnitude W bar Hermitian H bar square divided by k W bar Hermitian k W bar, which is also k square W bar Hermitian W bar into P over sigma n square, which is nothing but magnitude W bar Hermitian H bar square divided by W bar Hermitian W bar into P over sigma n square. So, what we have derived here is, if I scale the vector W bar by k, my SNR is still magnitude W bar Hermitian H bar magnitude square divided by W bar Hermitian W bar into P over sigma n square. That is because there is a k square in the numerator, there is also a k square in the denominator, and both of them cancel. So, this W bar Hermitian is scale invariant, that is, I can maximize the SNR up to a scale factor k, that is, I can maximize the SNR by choosing a vector W bar such that that is unique up to a scale factor, which means if I have any W bar, I can scale that W bar by a constant, it will still be an SNR maximizer. So, now instead of choosing any W bar, let me choose a particular W bar such that it has magnitude 1. So, what am I saying? I am saying I will choose to fix that scale factor, I want to choose W bar such that norm W bar square equals 1, implying W bar Hermitian W bar equals 1, because this is scale invariant, I can fix the scale. One way to fix the scale is to fix it saying magnitude W bar square is 1, which is W bar Hermitian W bar equals 1. So, now the SNR, observe this, SNR becomes magnitude W bar, let me just go to the previous page, SNR is magnitude W bar Hermitian square divided by W bar Hermitian W bar, but W bar Hermitian W bar has been fixed to be 1. So, SNR simply becomes maximize magnitude W bar Hermitian square into some constant P over sigma n square such that W bar norm square or W bar norm of W equals 1. This is the problem of choosing the beam former. We said the beam former SNR is invariant up to a scale, that is unique up to a scale factor. So, I am fixing the scale factor such that norm or magnitude W bar equals 1. Now, my problem is simplified to SNR equals or I want to maximize magnitude W bar Hermitian H bar square into P over sigma n square such that magnitude W bar equals 1, and this you will recognize now is nothing but, let me write it down, magnitude W bar Hermitian H square divided by P over sigma n square. I want to maximize this thing. Remember, this is nothing but the dot product of two vectors. This is A bar dot Hermitian B bar is nothing but A bar magnitude B bar times cosine of theta, where theta is the angle between these two vectors, and this is maximum when cosine theta equals 1 or theta equals 0, which means this vector a bar is in the direction of b bar, that is the angle between them is 0. So, a bar is in the direction of b bar, or a bar is some constant times b bar. So, similarly, this SNR here is maximized when w bar is some constant times h bar. Alright. So, we are saying the optimal beamformer is nothing but the antenna coefficient vector scaled by some constant. Alright. Which means now I know how to choose this constant. I have constrained my magnitude w bar equal to 1, which means c square norm, which means norm w bar square equals 1, or c square norm h bar square equals 1, which means c equals 1 divided by magnitude of h. So, now the received beamforming vector which maximizes the SNR is c times h bar, but c is 1 over norm h. So, the optimal received beamformer is nothing but h bar divided by norm of h, and let me write down that result over here. The optimal, remember optimal means something that has an optimality property, it is optimal in some sense. Here it is optimal in the sense it maximizes the receiver SNR. The optimal beamforming vector w bar that maximizes the receive SNR, the optimal beamforming vector w bar that maximizes the receive vectors receiver SNR at the output of the beamformer is h bar divided by norm of h bar. That is, let me denote this by a name, let me call this w optimal, that is the optimal beamforming vector is h bar divided by norm of h bar, and you can check this as unit magnitude, because norm w bar square is h bar magnitude h bar square divided by magnitude h bar square, which is 1. Alright. And further let us derive the SNR now. Now, the SNR we said is simply magnitude w bar Hermitian h bar square p over sigma n square. This is nothing but magnitude h bar Hermitian over norm h times h bar square divided by sigma n square. H bar Hermitian h bar is nothing but norm h square divided by norm h is norm h. So, this is again there is a square outside. So, this is nothing but magnitude vector h square, which is nothing but norm h square divided by p over sigma n square. So, this is the SNR. The SNR is nothing but magnitude of h square into p over sigma n square. We said this is the maximum SNR that is possible at the output of the receiver. This has a name. This combiner W opt, let me just go back here. This combiner W optimum that maximizes the SNR has a name that is known as the maximal ratio combiner. In a system, in a receive antenna system with multiple receive antennas, the beamforming vector given as h bar divided by magnitude h bar, which h bar is the vector of fading coefficients, is nothing but the maximal ratio combiner, and this technique has a name. This is known as maximal ratio combining. This technique has a name, it is known as maximal ratio combining or MRC. Now, also look at this, the optimal combiner is simply the channel coefficient vector divided by norm of H, or it is simply some scaled version of the channel coefficient vector. So, in a sense it is matched to the fading channel coefficient vector, and if you are familiar with your theory of digital communications, when you match the filter at the receiver to the impulse response of the channel, that has a special name, that is known as the match filter. So, this is essentially like a matched filter, except that it is a matched filter across the multiple antennas. So, it is the multi antenna matched filter, or it is also known as a spatial matching. The typical match filter you employ in digital communications is the temporal match filter, that is, you match the filter characteristic across time. Here you are matching the beamformer across the different receive antennas, that is across space, hence this is known as spatial matched filter. It has the SNR is norm H square P over sigma n square. This is the maximum SNR at the output of the receiver corresponding to the maximal ratio combiner. Let us take a quick example to reinforce this idea. Let me take an example. I want to consider an L equals to receive antenna system, that is my receive antenna system has L equals 2 receive antennas. So, let me again draw a schematic of that system, that has one transmit antenna and two receive antennas. There is link 1 between transmit antenna and receive antenna 1, and there is link 2 between transmit antenna and receive antenna 2. So, I am receiving two signals y 1, y 2. I can write this as y 1, y 2 equals h 1 h 2 vector times x plus n 1 and n 2 the vector. Alright. So, I have two receive antennas. I am saying y 1 the signal at receive antenna 1 is h 1 x plus n 1, y 2 the receive antenna signal at receive antenna 2 is h 2 x plus n 2. Now, let me take examples of these fading coefficients. Let me take h 1 equals 1 over square root of 2 plus 1 over square root of 2 j. Remember, let me refresh your memory, h 1 is a complex fading coefficient. Why? Because we are considering complex baseband equivalent systems. All right. Remember, even in the wireless systems we said that the h is a complex number. It does not mean that the signal transmitted is a complex signal, because that has no meaning. It just means that in the baseband these can be equivalently represented using complex numbers. All right. And h 2 is 1 over root 2 minus 1 over root 2 j. So, I am saying there are two fading coefficients corresponding to the two receive antennas. One of them is 1 over square root 2 plus 1 over square root 2 of j. The other is 1 over square root 2 minus 1 over square root 2 of j. Now, if I look at the magnitude, so now h vector is easy. I can write down the h vector as simply h 1 h 2. So, that is 1 over square root of 2 plus 1 over square root of 2 of j and 1 over square root of 2 minus 1 over square root of 2 of j. We said that h vector is L dimensional corresponding to the L fading coefficients at the receive antennas. The first coefficient is 1 over root 2 plus 1 over root 2 j. The second coefficient is 1 over root 2 minus 1 over root 2 j. Remember, the magnitude of each coefficient is magnitude of h 1, which is equal to square root of 1 over square root of 2 square, which is 1, which is half, plus 1 over root 2 of square, which is another half, which is half plus half, which is 1, square root of 1 is 1. So, magnitude of H 1 is 1. You can also compute similarly the magnitude of H 2 and you can verify that that is also 1. Hence, the magnitude of H bar vector square is magnitude H 1 square plus magnitude H 2 square, which is 1 plus 1 equals 2. Hence, magnitude H square equals 2. Hence, magnitude of H is nothing but square root of 2. Hence, the optimal MRC beamformer, let me write this as WMRC equals H bar divided by norm H. We know norm H is root 2. So, 1 divided by root 2 times H bar is the MRC combining vector, which is 1 over square root of 2 plus 1 over square root of 2 times j, 1 over square root of 2 minus 1 over square root of 2 times j, which is nothing but 1 over square root of 2 into 1 over square root of 2 is half and so on. So, this is half plus half j, half minus half j, and this is the MRC, maximal ratio combining. This is the maximal ratio combining vector. Alright. Now, we know given the maximal ratio combining vector, the output of the received beamformer is nothing but W bar Hermitian y bar, and we said, let me remind you how W bar looks. W bar is the optimal MRC combiner which has this structure. So, W bar Hermitian, which means I simply have to take the transpose and then conjugate. So, if I take the transpose and conjugate, this is simply half minus half j. I am taking transpose and then conjugate. The other element is now half plus half j times y bar, which is y 1 y 2, and this I can write this equivalently as half minus half j times y 1 plus half j times y 2. All right. So, this is nothing but this here, this box here, nothing but the output of the beamformer. So, what are we saying? We are saying we started with a channel which is given as with 2 receive antennas, one with fading coefficient 1 over square root of 2 plus 1 over square root of 2 j, the other with fading coefficient H 2 1 over square root 2 minus 1 over square root 2 of j. We computed the optimal beamforming vector, that is we said it is 1 over 2, that is half minus half j, half plus half j and half minus half j, and we said the output of the beamformer, the output of this optimal beamformer, which is also the maximum ratio combiner, is half minus half j times y 1 plus half plus half j times y 2. So, I am taking the signals across the 2 receive antennas y 1 and y 2 and combining them, so that I can now detect the signal. We also said this is maximal ratio combining or also the spatial match filter. So, I would like to conclude my lecture with this today. We have developed the theory of multiple antenna systems and the optimal beamformer, maximal ratio combiner, so on and so forth, and I will conclude my lecture at this point and carry on with the bit error rate. Remember, we still have to carry out the bit error rate analysis of this multiple antenna system. So, I will start with that bit error rate analysis of our multiple antenna system in the next lecture. Thank you very much.